All right, today we're going to start our study of limits. And this is our very first unit in calculus. Now remember, limits are the foundation of calculus. So it's very, very important that you understand everything we're talking about in this unit, or you're going to be lost for the rest of the school year. Now, when we're looking at this unit, I want you to study on 3 essential questions that you should be able to answer by the end of this unit. And those are, what is a limit and why are they important? What strategies can you use for finding limits? And what roles do derivatives and limits play in the foundation of calculus? But today we're only going to focus on our first objective. In today's lesson's objective, we're going to look at finding limits using numerical values from a table and from looking at a graph. For our first example today, we're going to look at finding a limit numerically, and that means plugging in these function values into our equation and seeing what we get. So our first example, f of x is defined by f of x is equal to x squared. So let's see what f of x equals when x is equal to 2.9. So using my calculator, I plug in 2.9 quantity squared, 8.41, and then plugging in 2.99, we get 8.9401. And then finally, we get 8.9994. Now notice that I'm approaching the value of 3, and all of my following equations focus on x equals 3. And I'm approaching it from values that are just a little bit smaller than 3, but very close to it. So we call this approaching from the left. So when you approach values, and notice I'm getting numbers in the neighborhood of 3, very, very close to 3, but smaller than 3. So now let's go in the other direction. Starting at 3.1, then 3.01, 3.001, I'm getting closer, numbers closer to 3 from the other side. So when I do 3.1 squared, I get 9.61, and then 3.01 squared is 9.0601, and then 3.0001 squared is 9.006. Using these numbers x plus 3.1, 3.01, 3.001, notice I'm getting numbers just a little bit larger than 3. So we call this approaching x equals 3 from the right. All right, let's look at part B. What do the values tell you about f in the neighborhood of 3? So that means numbers very, very close to 3. So I'm looking at, as my x is getting closer and closer to 3 from the left-hand side, I notice my y values are getting larger and larger, and they're getting closer to, looks like, about a 9, because I got 8.94, then I got an 8.994. So I'd say those are getting close to 9. Now look from the right-hand side, I got 9.61, 9.06, and 9.006. So this appears to be getting closer and closer to 9 as well. So I'd say it looks like in this neighborhood of x equals 3, it appears that f of x is approaching 9. As x is approaching 3. That arrow is read as x approaches 3. Looking at 3, based on this chart above, what do you think the function value is at f equals 3? Well, I would estimate that I think the function value at f equals 3 should be 9. Part D, what is the function value at 3? So to figure out the function value at 3, all I do is take 3 and I substitute in place of every x into my equation f of x. And so I get f of 3 is equal to 3 squared, which is 9. So my estimate was correct in this case. Okay, now let's look how I could write this information using some calculus notations. So I want to say that f of x is approaching 9 as x gets closer and closer to 3 from the left and closer to 3 from the right. So our calculus notation, that is what a limit is. A limit is what the value of the function is approaching from each direction, from the left and from the right at the same time. So in calculus notation, I would write that the limit as x approaches 3 of my function f of x is 9. And that's answering what's happening in the neighborhood of 3. All right, let's do one more example like this. In example 2, our function is g of x, which is defined by x cubed minus 3x squared divided by x minus 3. And I'm going to do the same thing. I'm going to use my calculator to plug in each of these values into that g of x function. 2.9, 2.99, 2.999. You can pause the video and do this on your own, and when you're done, come back and we'll see the answers. Okay, for part B it says, what does the value tell us of g in the neighborhood of x equals 3? So as we're approaching it from the left-hand side, we're getting closer and closer to 9 as well, and from the right-hand side, we're getting closer and closer to 9. So I would say as x approaches 3, f of x approaches 9. Based on the chart above, what do you think the value of g of x is? Well, using our information above, I would have to estimate that the value of g of 3 is 9. Well, let's actually figure out the value of g of 3. So I go to my g of x function, replace every x with 3, and then we're going to simplify this equation. So we have 3 cubed minus 3 times 3 squared over 3 minus 3. Well, on the top, 3 cubed is 27, minus 3 times 9, which is 27. So I got 27 minus 27, which is 0, divided by 3 minus 3, which is 0. So I got 0 divided by 0. So you learn in earlier classes when you have division by 0, this is called undefined. But that's not exactly undefined. What you're going to learn later, this is called the undeterminate form, and we're going to learn some calculus techniques to get around this. But for now, we'll just say that g of 3 does not exist. E, is there a way to mathematically communicate the results from the chart above? Yes. Using limit notation, we can talk about what's happening to the function as it gets closer and closer to x equals 3, even though the function value at 3 does not exist. So let's start from the left-hand side. The limit as x approaches 3 from the left of g of x, which is our function, is equal to, well, it's getting closer and closer to the number 9, so we say that's equal to 9. Now, one thing I want you to notice is I use this new notation here. I said with this little negative sign here, that means from the left. So anytime you see as x approaches 3 from the left is how you would read this. The function is approaching 9. So the limit as x approaches 3 from the right, which is the plus sign of g of x, is also equal to 9, because from my table it's getting closer and closer to 9. So when you see a little plus sign, a power that's a plus, you would read this as from the right-hand side. And since my limit from the left and my limit from the right is approaching the same constant, the 9, I can therefore say that the limit as x approaches 3 of g of x is equal to 9. So when I do the number without a plus or minus sign, that means it's approaching the same number from the left as it is from the right. Now that you know how to find limits using a table of values, let's look at finding limits graphically. Now the first thing you have to know is in order for a limit to exist at a number, the limit from the left and the limit from the right must approach the same number. So notation-wise, this is what I'm writing down here. The limit as x approaches a from the left of f of x approaches the number L, and the limit as x approaches a from the right of f of x approaches the number L. Therefore, we can say the limit as x approaches a of f of x is equal to L. Now that we know how to note this, let's look at some of the graphs we have above. And I want to look at this f of x, and I want to figure out what the limit as x approaches 1 is. And so what I need to do is I need to approach the 1 from the left-hand side and see what y value it's getting closer and closer to. And then I approach the 1 from the right-hand side and see what value it's getting closer and closer to. Only if it's approaching the same value can I say the limit exists at 1. So looking at this left-hand side, the limit as x approaches 1 from the left of my function value f of x appears to be getting closer and closer to 3. So I'd say the limit as x approaches 1 from the left of f of x equals 3. So now let's look at x values closer and closer to 1 from the right-hand side. Well, it appears my graph is also approaching 3 from the right-hand side. So the limit as x approaches 1 from the positive side of f of x is equal to 3. So since the limit from the left is equal to the limit from the right, I can say the limit as x approaches 1 of f of x is 3. Okay, for the second graph, we're going to look at the limit as x approaches 0 of f of x. So here's 0, and we're going to approach, it looks like we're getting closer and closer to a y value of 2 from the left-hand side. So the limit as x approaches 0 from the left of f of x equals 2. Now let's look at from the right-hand side and see if it's approaching the same number. So as I'm getting x values getting closer and closer to 0 from the right-hand side, I have the limit as x approaches 0 from the right of our f of x function appears to be also approaching 2. So since the limit from the left equals the limit from the right, I can say the limit as x approaches 0 of f of x is equal to 2. Okay, let's look at examples C and D. So for example C, we're looking at the limit as x approaches 2 of f of x. So notice as I'm approaching from the left, it appears that my y value is approaching 1. Actually, it's staying constant at 1. And then when I'm approaching it from the right-hand side, my y value is also approaching 1. So I'd say the limit as x approaches 2 of f of x must equal 1. Now notice this has absolutely nothing to do with the function value. Even though the function value at x equals 1 is down here at 0, x equals 2 is down here at 0, it means nothing. I want to know what's happening to the function as it gets closer to that value 2, not what's actually happening at 2. That's the difference between a limit and a function value. Okay, looking at this next example, we want to find the limit as x approaches 0. So let's look from the left-hand side here. And it appears that our y value is approaching -1 as x is approaching 0. And looking at the right-hand side, it appears that our y value is approaching 1 as x is getting closer and closer to 0 from the right. Now, since 1 and -1 are not equal, I would say the limit as x approaches 0 of this function f of x does not exist. Our last two graphical examples, let's look at the limit as x approaches 0 of 1 over x squared. So as we're approaching 0 from the left, notice that my function value is getting exponentially higher. So it's getting up, it's going up, 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 up. And so we would say the limit as x approaches 0 from that left-hand side is going toward infinity. As the limit as x is getting closer and closer to 0 from the right-hand side, notice my graph is also getting exponentially higher. So I'd say the limit as x approaches 0 from the right of 1 over x squared is also approaching infinity. So notice that from the left, my function is approaching infinity, and from the right, my function is close to infinity. So I could write this as the limit as x approaches 0 of 1 over x squared is equal to infinity. Now, that's one way to write this, and this is the way I kind of want you to write it because it tells me a little bit about what's happening to the graph. They're both going to infinity in the same direction. They're both going up, and it tells me that I must have an asymptote here at x equals 0. But since we can never actually reach infinity, we can also state this as a limit as x approaches 0 of 1 over x squared does not exist. Either answer is technically correct, but for this class, I want you to use infinity as your answer because this tells me so much more about the graph than does not exist. So please, if they're going both in positive infinity or both directions going in negative infinity, note that in your answer instead of just writing does not exist. Okay, looking at our last graphical example, we have the limit as x approaches 0 of sine of 1 over x. So as we get close to 0, notice what's happening here. This number is bouncing up and down, up and down, up and down in between -1 and 1. And as we're approaching it from the other direction, it's also bouncing up and down from 1 and -1. So if it's just oscillating in between these two values and never actually reaching a single value, we call this an oscillating function, and the limit does not exist. As the last three examples illustrated, there are three cases in which a limit fails to exist, and you need to be aware of all three cases. The first one is the function value approaches a different number from the right of c as it approaches from the left of c. So if the right-hand limit is not equal to the left-hand limit, the function value at c does not exist. The second case is if the function value increases or decreases without bounds as x gets closer and closer to a value of c. Increasing without bounds and decreasing without bounds, that translates to infinity or negative infinity. So if it's approaching infinity or negative infinity, then we know the function value does not exist. The limit does not exist at that value. The third case is if f of x is oscillating between two fixed values as x approaches c. So a function oscillates. Remember, oscillate means that it's bouncing up and down between two fixed values. So if it's oscillating, we also know the function does not exist. Pause the video and try to work out these examples before pushing play. All right, let's check your work. So part A, what is the limit as x approaches -2? So from the left of -2, I appear to be going to infinity. And from the right, I also appear to be going to infinity. So limit as x approaches 2 of f of x equals infinity. Part B, we're looking at it's approaching x from the left, 2 from the left. And that appears to be about a 5. So I'd say the limit as x approaches 2 from the left of f of x is 5. Now what is the function value at 4? The function value, as I go to 4, and I want to know what exactly the value of the equation is. And it appears to be 5. And then now let's look at the limit at 4. So what's happening from the left of 4 and from the right of 4? They have to be approaching the same number for that to exist. And they are. It's 5. And what's the limit as x approaches 11 from the right? So 11 from the right is not this one, but this side, because I'm approaching that higher value from the right. So it's also equal to 5. The limit as x approaches 5 from the left. Here's our 5, and from the left of 5, we appear to be going up to infinity. Well, but what is the function value at x equals 2? So at 2, I want what the function equals to, which is the dot here at 4. The limit as x approaches 6 from the right. So let's find 6, and we're approaching from the right, so that means we must be approaching here, which appears to be about a height of y equals 3. And limit as x approaches 6 from the left-hand side. Oh, that's only a value of 2. The limit as x approaches 8 of f of x. Here's our 8. And it looks like we're approaching from the left and the right the same value of 3. And then the function value at -2. Well, the function value at -2 is this dot, which is a height of 2. And the limit as x approaches 0 from the left of f of x. So going from the left-hand side of 0, and it appears our function is also approaching 2.